Fred.
I'm Tatiana.
My name is Ty, and today we'll be talking about quantum dot on chip lasers. The current situation and problems. As you may know, we've been using silicon chip and metal circuit to transfer data. Although this is what we're using right now, it is very limiting in some way. So our research and the improvement that we can make on this research will definitely help on the following reasons. The first is the cost efficiency. With this research, we are trying to basically, so with this we will cut down all the material used on building circuits. The second will be data flow. Instead of using electricity, we'll be using light, and because in light we have many different kinds of wavelengths that they don't interfere with each other, we can put all this into one single circuit. Number three is eco-friendly. It will be cutting down the energy used on resistive heating, so we don't have to waste all the energy on cooling all the system and all the circuits come up. So what are semiconductors? Briefly, are just material that turn light into electricity or the other way around, electricity into light. For example, solar panel are components that turn light into electricity, and lasers are to the other way around, turn electricity into light. And for the background, as you may know, this is only one kind of electricity, but with light, like I said before, they have many different kinds of wavelength, and we can combine all of them into one single circuit instead of many different circuits like electricity does. And on the graph on the left, we can see all kinds of wavelengths such as radio, microwave, infrared, ultraviolet, and X-ray, and how they behave as a wavelength. And over there we just have data being transferred.
So to be able to send light with silicon semiconductors, first we need to unprocess the silicon chip. Next, we would have to use certain acids to etch trenches within the chip. And after that is done, we would use laser quality gallium arsenide to be grown inside the trenches within the silicon chip. And then we'll place gallium arsenide quantum dots grown on the gallium arsenide. We cannot grow quantum dots on the silicon because, there has not been methods yet to grow gallium arsenide quantum dots on silicon, so we grow gallium arsenide quantum dots on gallium arsenide. So the first process of wet etching the chip needs to be done in a very clean and sterile environment with very few particles. So it's usually done in a clean room. And so this is our mentor. She's about to etch the chip in hydrofluoric acid because hydrofluoric acid is able to cut through the silicon. But before that, she cleaned the chip with potassium hydroxide. And so after we create these etches within the chip, we have to make sure that the etches are of quality. So we use a scanning electron microscope to see the trenches. So you put a sample in the vacuum within the microscope, and the electrons hit the sample, and the electrons get scattered off of the sample, and then the detector sees the electrons, it captures the electrons, and it's able to produce an image. It's similar like taking an image that you use a flash on. The light hits the object and the light bounces back and you're able to get the image. So this is a SEM photo of our chip. This is the edge of the chip. And we have, these are our trenches. They're roughly 1.1 microns wide. And so we need these just to grow the gallium, the layers of the gallium arsenide. So then after we do this, we also use atomic force microscopy, which is AFM, and we use this, we put force on top of on the chip, and we measure how much force is being pushed back, and that can be translated to giving us the different heights within the chip to make sure that the trenches are uniform with the height difference. And so once it's determined that the trenches are pretty uniform, then we fill the trenches with gallium arsenide. So we need this gallium arsenide to grow the quantum dots. So the gallium arsenide and this is being filled to be roughly level with the silicon, and they're trying to be grown at uniform rates.
So as far as growing quantum dots, we use an MBE, molecular beam epitaxy, and we basically put our sample in a very low vacuum chamber, and to roughly describe what it does, it basically coats in thin layers the substance we're trying to put onto the sample. And depending on the time, temperature, and pressure we use, we get different types of characteristics of gallium arsenide quantum dots, and that determines the wavelength we're going to get. This is an image that we have using AFM of the quantum dots that we grew. As you can see, these quantum dots are pretty uniform. We are trying to optimize it to get them all uniform to dial in the wavelengths we want to send data. And this picture represents that we have come pretty close to it, and it is valuable data for what we are studying. And from there, we measure the electronic and photo-optic qualities of the quantum dots using a process called photoluminescence spectroscopy. And that is basically a microscope that takes a super cooled laser to optimize the laser's energy, goes through an optical system like a lens, and it hits our sample, and it reflects off the sample through another system of lenses and gets measured through a spectrometer that measures things like the wavelength of the quantum dots and the intensity of the light they give off. And the data that we get is displayed to us on the computer. And we want to study this essentially because we are trying to dial in, again, specific